All right, so today we're going to start on the next module, Module 7 we're at. You'll be working on Module 6 throughout this week. That is pointers, pass by reference, error handling in both languages. But the one after that is arrays and collections. Now, both languages have arrays. Java has collections, and that's what we're going to be focusing on with respect to Java. We will cover arrays in Java, but then we'll quickly leave them behind. Yep, just making sure everything works. So what are arrays and what are collections? It is rare to deal with only one thing, right? One piece of data, one integer, or one double, right? Or one character. Instead, collections of data are are needed to store multiple instances of those things, right? Whatever your data is. If it's a collection of numbers, fine. If it's a collection of integers, fine. If it's a collection of other things, which we'll eventually get to, then so be it. You need a collection to hold that stuff, right? In C and Java, we use arrays to store collections of similar items, elements, right? Things of the same type. So in both languages, if you create an array of integers, it can only hold integers. If you create an array of doubles, it can only hold doubles, right? Et cetera, et cetera. In some languages, you can have what are called mixed types. For example, Python, PHP, you can have a collection where the first thing is an integer, the second thing is a double, the third thing is a string, right? You're mixing the types into this collection. That's not supported in either language, right? At least it shouldn't be, right? I'm not even going to show you how to do it. It's a hackish way of doing it. It's like 15-year-old Java. In general, for both languages, arrays have a single name, that is an identifier. The array of things that you are holding, right? You can access individual elements using an index. Right? An index is an integer. Access. An index is an integer that represents the ordinal or the placement of an element. Indexing in both languages starts at 0. And we'll look at an example later on, or a demonstration later on, of why that is. In computer science, most things start with 0. I don't know how many people took the AP exam for computer science. Did anybody take it? Okay. I was just a reviewer for it over the weekend. I didn't grade or anything like that, but I took a look at it. And it was weird to me that, I think it was an influence of Scratch, actually. Has anybody used Scratch in high school? Okay, so where does it start? Does it start at 0 indexing? The first element is at index 0? Nope, it starts at 1. Why? Who knows? That, and only one other language that you probably may have seen before, start at 1. Has anybody done Roblox programming? Oh, nobody? Okay. All right, so you can do, you can put together a Roblox game. People played Roblox, right, when you were a kid? Yes? No? All right. Well, when you program that, that's in a programming language called Lua, L-U-A. And it's another one that starts indexing at 1. Those are the only two common programming languages that I would say start their indexing at 1. The vast majority of programming languages start at 0. So it was kind of weird, and I put that in a comment that, well, if you're using Python or Java in a high school curriculum, and then they get to an AP exam in which it's a Scratch influenced and they start using 1 indexing, that might be able to trip them up. I don't know, maybe not. But the first element is at index 0. Right? The second is at index, well, you go in order, they are integers, the next one is at 1, etc. Right? If there are n elements in an array, the last one is at index, tell me, So if you start at 1, of course, the last one, and there are 5 things in there, 1, 2, 3, 4, 5, the last one will be at index 5. But if you start at 0, like the vast majority of programming languages, where do you end up at the last one? N minus 1, right? So you've always got to make sure that you stop short. To access an element, use the square brackets. So for example, again, the first element is going to be at, if our array is called ARR, short for array, then the first element is at index 0, right? You can go array sub 1, right? Dot, dot, dot. You can access an array element using a variable, right? Array sub I, right? Use a variable on index variable. And now we know why we've been using I this entire time. What is I short for? An index that you're going to use in an array, right? And then finally, the last one, the last one is going to be at array sub n minus 1, where n is being kept track of depending on the language that you're in, okay? So let's go ahead and get into it in arrays in C. We'll start with what are called static arrays, right? We'll start with static arrays. Right? Arrays that are allocated on the program's call stack. Right? And then very, very quickly, let me go ahead and give myself some more room here. There we go. And then very, very quickly, we're going to abandon them. Right? This is just to get us started, okay? Very quickly, we will see the limitations of static arrays. Now, we've already seen the keyword, the term static before, as opposed to dynamic. A static analyzer is a code analysis tool that looks at your code before it gets compiled, right? It's looking at the code as a static thing, an unchanging thing. Dynamic analysis tools are when the program is actually running, Valgrind, right? Because it's dynamic, it's changing. Not that arrays can't change, but this is a different static, right? It means that it has been allocated on the call stack, okay? So let's go ahead and jump over here to the demonstration, right? The environment over here. And let's go ahead and create an array that can hold 5 integers, right? Int array sub 5. There we go. So the syntax there is that it's just like a regular old variable declaration, int x, right? But instead of just ending it there, what I'm going to do is I'm going to put square brackets, and then that 5 there is indicating the size of the array. How many things can this hold? It can hold elements in 0, 1, 2, 3, 4, right? So let's go ahead and assign those values, right? Assign some values, dot, dot, dot. Array sub 0, we'll go ahead and set that equal to 42. Array sub 1, we'll set that equal to 101. Let's set the last one here, which will be last one, question mark. What index variable, or what index am I going to use there? For the last one? If there are 5 of them in there, it starts at 0, 1, 2, 3, 4 is the last one. And I'll set that equal to, I don't know, 37, right? There we go. And then you can also, iterate over an array using a regular old for loop. Why did I immediately jump to a for loop? I know exactly how many things are in the array, right? So for each one, right, it's how you would actually say it. For each one in that collection, just go ahead and use a for loop. For int I equals 0, I is less than, in this case, 5, I plus plus, an idiomatic for loop here, right? Where you start at 0 and you go up to, but you do not include the size of the array. Right? This will stop at I, the last iteration here will be I is 4, which is exactly what I want, the last element. Printf, array sub %d is equal to %d and the line, where I'm going to print the index variable and then the value stored in that array. There we go. Now, before I actually compile and run this, help me predict, what is this going to print out? Well, I set the first one 42, set the second one equal to 101, and the last one to 37, but what about 2 and 3? Did I set those values to anything? Nope. So by default, what in C, by default, what variable values are assigned? Is there a default? Right. Remember, question mark, garbage, dead beef, likely 0, but let's find out. It all depends on the system. Right? All right, so I got away with it and there were zeros here. What if this was much, much larger? 5,000. Right, there we go, 5,000. All right, I'm only setting the first two and then the fourth one there, not the last one anymore. Let's go ahead and see, is it the case that they're all going to be 0? Most of them, except that some of them are what values? Did I ever set those values? Nope. So what is that? Again, garbage, dead beef, who knows, undefined, right? So some observations here already. I'll make sure that we copy that code over later. Observations, right? As with regular variables, no default values are set in an array, right? Could be 0, could be garbage, etc. Right? What else do I want to observe? Oh, you can use an idiomatic for loop, right, to iterate over the elements in an array, right, etc., etc. Okay. Before I copy that over, let's go ahead and try one more thing here. So not 5,000. Let's go ahead and go with 5 million. So tell me how many bytes does an integer take? Do you remember? 4. So 5 million bytes, or 5 million integers would take how much memory? 20 million bytes. That's a little less than 20 megabytes. Okay. Let's go ahead and set the last one here, 5 million minus 1, equal to 37. And then I don't want to print them all out, so I'll just go ahead and comment that code out for now here. Right? And let's see what happens when I try to do this. Okay? Predict what's going to happen. Now, am I illegally accessing an element that doesn't exist here? Probably not. No. I'm accessing the first one. I'm accessing the last one. But I still get a segmentation fault here. Right? Limit u. Is it u limit? Or it's u limit, isn't it? Yeah, u limit a. There we go. Sorry. U limit a. There we go. And is there a stack? Find stack. There we go. So remember when we covered functions, we covered how programs work. When a function calls a function, remember that these stack frames get created. Right? This stack here, this program stack, is very, very limited. This is telling me that it's actually limited to 8 megabytes. That's how many kilobytes it is, 8,192 kilobytes. Right? So roughly about 8 megabytes. Okay? You tried to allocate, what did we say, a little less than 20 megabytes on the program stack. That would be like putting dish after dish after dish after dish. It only holds 50 dishes, but you decided to go ahead and go up to 500 dishes. Right? So what's going to happen to your stack if you fill it up too much? Fill it up and go beyond. Right? What happens to your dishes if they're stacked too high? It's going to fall over. What do we call that with respect to a stack? It's filled, and then the water, think of it as water. You put more water in. What does the water? What happens to the water? It overflows, giving you a stack overflow. Right? That's where they get their name, right? Stack Overflow. So what I've done here is I've created something that's too big, right? Another observation here is that the static arrays are allocated on the program stack, which is limited, say 8 megabytes. And that's just this particular system. If you are on an embedded system or something with even higher resource constraints, right, smaller memory, it could be as low as 1 megabyte, or maybe even measured in kilobytes. Go back 30, 40 years, and everything was measured in kilobytes. So no way were you going to be able to do this, right? Allocating too much memory, large arrays, on the stack is not possible. Okay? So we're going to quickly, like I said, very quickly, we're going to see the limitations of static arrays here and end up, not being able to do this. Let me go back to the 5,000, though, that worked here. 5,000. There we go. Okay. Now, I can iterate over this just fine because we did it before. GCC. And let's run it. And we'll still see that there's garbage here eventually somewhere in some places. That's not what I want to focus on, though. What I want to focus on is be careful with indexing. What if I did something like this? Array sub -1 is equal to 42. Array sub, I don't know, 6,000 is equal to 42. So are those indexes that exist? If indexing starts at 0, can you go negative? Nope. You think of it like this chunk of memory, right? And that's your world. If you go negative, then you've fallen off the edge of your world, right? If you go too much, then you've fallen off the edge of the other world, right? It's a flat Earth kind of thing, right? Sorry to dispel it. The Earth is not actually flat, but your arrays are flat, and you can fall off of either side, okay? Let's find out what happens when I attempt to do something like this. First of all, hopefully the compiler, nope, the compiler, even with all warnings on, is not going to say, you can't do that. It's your memory, do with it what you want, right? When I try to run this, darn it. It ended up being just fine. Okay, jump all the way to the, here. Let me not go 5,000. Let me start at -1 and then go up to 500. Maybe it will work. Let's cut that down even to just 5 here and see what happens. It worked. So maybe you can do negative indexing. Think about what's happening here. Where did that array get allocated again? On my program stack, right? Say that there are only 5 elements here. Say just 5, right? And I'll go with the original values here. There we go. Now we're all the way back here at the beginning where we only have 5 integers here. That's allocated on the stack. 0, 1, 2, 3, 4. Where's -1? It's 1 right before here, right? 4 bytes right before this first one. I wrote -1 to those 4 bytes. In other words, I overwrote my own memory, my own stack space memory. It's going to let me do that. It's your memory. Do with it what you will, right? If you get too cocky about that, though, and you try to overwrite memory that doesn't belong to you, say -6,000, let's find out what happens now. I'm pretty sure that this is probably out of the scope of my own memory space. Oh, no, it's not. All right, fine. 60,000. I just have to go big enough here. Oh, nope. Okay. You can do with it what you want. 60. Oh, probably because I'm not accessing it. That's why. Nope. All that memory belongs to me, apparently. And you can screw it up as much as you want, right? Undo, undo, undo. Let's go positive 6,000. I'm hoping for what's called a stack smashing event here, or a segmentation fault here. Finally, what I ended up doing is I tried to access something that was way beyond the memory that I had allocated, and it detects that and says, no, you can't do that, right? So going beyond your indexing is also undefined behavior. Even when it was working, right, I was still screwing up my own memory. It just wasn't actually apparent to me until, because it didn't end up with a segmentation fault, right? Still, it's going to result in errors, in unexpected results and stuff like that. You could get away with it, right? But hopefully you won't get away with it, right? Accessing values outside of the array, that is negative index values or index values that exceed the size of the array, are undefined behavior, right? They could end in a segmentation fault. They could simply end with garbage results. Or you could get away with it. Even if you get away with it, it doesn't mean that it's going to be a good idea to do something like this. I wasn't getting away with it here. Let's go ahead and go with 60. Am I getting away with it here? Let's find out. It looks like I'm getting away with it. But remember that you can run valgrind, and that will have a much more reliable report on what's going on here. Right? In fact, it says that there were 10 errors in 5 different contexts. Do you see that way down at the bottom? Here's the big report that says you can't do this. This value was created, uninitialized value was created as a stack allocation in main. I didn't compile it with the G flag, and so it's not going to tell me what lines these numbers are on. But I've got a whole bunch of issues here because I am attempting to access memory outside the scope of what was allocated, outside the scope of that array. Even though it ended, right, it gave me some values. Valgrind here is still able to detect, nope, you're accessing memory that doesn't belong to you. Okay? All right. So be careful with indexing. This is bad. Right? So don't do that. I'm going to go ahead and cut and paste this, and you'll have it over here in your notes. There you go. All right. So questions so far? What about static arrays in Java? So static arrays in Java. They don't exist. Don't worry about them, right? We're going to get away from a static arrays almost immediately here. And why? Because Java doesn't even support them, right? So instead, what we're going to want are dynamic arrays, right? Dynamic arrays, ... But before we do that, let's come back up here to static arrays and look at maybe some very limited use cases, right? So instead of observations here, times that static arrays are okay or good, right? When you have a limited number of values to store and you know them up front. So for example, let's go with a static array of the first 10 primes, right? The first 10 primes are not changing, right? They're fixed. And so it makes sense that you can put those into an array. Here's the syntax for doing that, right? Primes. I am not specifying the size of the array here. I could if I wanted to. In fact, let's start out by doing that, 10, okay? And I'm immediately setting it equal to something. I use the opening and closing curly brackets here to do so. So tell me, what are the first 10 primes? I'll get you started. 2, 3, 5, 7, 11, 13. What else? 17, 19. Oops. Comma, 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 comma. How many is that? 4, 8. 2 more. 23. Not 24, 25, 26, 27, 28, 29, 29. There we go. They're the first 10 primes. Right? Now, the way that all of that is perfectly 100% initialized. Whereas before with the static array, it could hold garbage, right? It could hold 0, it could hold whatever. I am saying immediately assign all of these values to those array elements. The first one at index 0 will be 2. The last one at index 9 will be 29, right? And each one of them is delimited by a comma. I end that with a semicolon at the end. Well, compilers are dumb, but they're smart enough to count. If you were a compiler and you came and said, okay, well, how big does this need to be? All you have to do is look at the number of commas. That tells you how many things are in there. And you know, oh, okay, well, this is going to be an array of size 10. You're smart enough to figure that out as a compiler, right? So you do not need that 10 in there. Right? It's optional. You can put it in there, right? You can make a mistake and make it smaller than it should be, and the compiler will probably check that and say, nope, you can't do that. Let's find out. Hopefully we've got a smart compiler here. Yep. So what's wrong? Excess elements in the array initializer. You said that it was of size 5, but so I was able to assign the first 5, but the last 5 I ain't able to do that. Right? You can make it bigger, 50, right? And then you have the same problem as before. This is just a warning that I'm not actually using that variable there. But this will be of size 50. The first 10 of them will be as assigned right here. What about the last 40 of them? Question mark, 0, garbage, who knows, right? So why bother with that at all? Just elide it. Elide. Is that how you spell it? Elide. I think it's 2 L's, isn't it? Elide, or it is 1 L. Excellent. I got it right. Elide or Elysian. There's 2 S's. Nope, there's 1 S. I got it right the second time. Good. Cool. I earned my spelling star for the day. Elide or Elysian. What is that? Define. Elysian. Here's your 50-cent word of the day. Omission of a sound that would normally be pronounced in a speaking word. So you know all this already, right? You just didn't maybe have a word to describe it yet. So what'd you do this weekend? You know what did I do there? I elided some things, right? You do it without thinking about it. What'd ya, right? How would you actually spell that? What did you, right? But if you spell it like I sounded it out, what'd ya, right? What'd you do this weekend? That's eliding. Instead of enunciating each one of those syllables, what did you do, right? I guess what did you do, right? I elided all of that away. Every language does this, by the way. And it drives people nuts that are trying to learn that language, because there's a difference between the textbook learning, where you learn the proper grammar and enunciation, and then you go out and nobody speaks that way, right? Every language does that, including programming languages. Right? You take away the unnecessary things. If a compiler can figure out that there are 10 elements in here, you don't need to provide that. You can elide it away. Right? And that's referred to as elision. Okay? There's your 50-cent word of the day. Right? Don't worry about it. Right? Just understand that there are those concepts all over the place. Every concept that you have in language, verbs, nouns, grammar, punctuation, there is some sort of an analogous concept within programming languages. Why? Because they're human created, right? We created them from our own minds, and so at least in the back of our minds, we were always thinking about how does our language work? That's how a computer language should work, right? So anthropomorphism, right? Trying to assign human characteristics to it, right? Even though it's not human. Okay, any questions so far? I wonder, can you at least do this in Java? Let's find out. Yes, you can. That is not a static array, though, right? Though it looks like a static array, it is not. It is not. There we go. Right? It is a dynamic array. So what are dynamic arrays? Dynamic arrays are not allocated on the stack. Dynamic arrays are allocated on a different spot called the heap. Right? The heap is a much larger area of memory. Right? It is not limited to that 8 megabytes that we did the U limit on. I don't think that there is a U limit equivalent of the heap. Let's see, data segment size. Yep, unlimited. Max memory size, unlimited. Real-time max user processes, unlimited. Pretty much we're unlimited on anything. Now, unlimited means that the operating system will allow you to access as much memory as you want. When the operating system itself runs out of memory, then of course you have a limit, right? If you only have 8 gigabytes of RAM or something, right, you're going to run out. Then that's where it goes to virtual memory, and stuff is being stored on disk and secondary memory and stuff like that. So virtual memory, you will not hit those limits in this class at all. But that's why it's saying unlimited. It's still limited, right? We live in a finite universe. You can't have an infinite amount of memory. Likewise, you can't have an infinite amount of memory on your computers, but unlimited simply means that it's going to let you do as much as you want until it dies, right? It'll keep on giving, right? The heap is a much larger area of memory, but less organized, as the name suggests. So a stack, the way that we've been talking about a stack, is this nice stack of dishes, one on top of the other, right? That means organization to me, right? That means that there's a stack frame, and then on top of that is the very next stack frame, and you can pop that off and return back to the calling function that you were originally started in. But a heap, what comes to mind when you think of a heap? A pile, right? A disorganized pile. What do you do with a heap? You just do you nicely put something where it belongs in the heap? No, it's just a heap of clothes. You throw it on the top and maybe it rolls down a little bit. Maybe it stays on the top. Maybe it rolls down halfway or all the way to the bottom until the heap grows and grows and grows, right? So it's a little bit less organized. Now, it's still highly organized because it's a computer, so it's not like a heap of dirty laundry or something like that, where it's completely disorganized. It's just a little bit less organized, right? In C, you allocate memory on the heap by asking the operating system for a chunk of memory of a particular size. And I'm going to emphasize that. For example, you want to store, say, 100 integers. How many bytes should you request? Remember that an integer, how many bytes is an integer? 4. So you would need to request 4, going to code mode here, 4 times 100 bytes of memory. All right? To do so, you use the memory allocation function, right? So what did I highlight there? M and alloc. The memory allocation function is malloc, right? That's what it stands for, memory allocation, okay? It has the following signature. Let's see. It has the following signature. There we go. Void star malloc size t int, right? So let's go ahead and look at each one of those in turn. First of all, size t can be thought of as an integer, right? Ignore that actual type. The size t is a size type. In other words, there are old school systems where a byte was not 8 bits. Instead, it was 7 bits or something like that. And so, for historical reasons, you needed this additional value type here to indicate how big is a byte, or how big is this memory, or whatever. Don't worry about it. Treat it like an integer, right? You can treat it like and in fact, we will treat it like an integer, right? What about the return type? The return type is a generic void pointer. Oh, what is that? Void star. Well, what is int star? What type is that? Int star would be a pointer, right? A pointer to what? An integer, right? What is double star? That's also a pointer. A pointer to what? A double. So, what is void star? It's a pointer. A pointer to what? Anything. It is a pointer to anything. Right. A void pointer is a raw memory address. it can point to a memory address that stores an int, or one that stores a double, etc. It can point to anything because it's just a raw generic memory address. So why do we have malloc returning a raw memory address? Here's how it works. You ask malloc for a certain sized chunk of memory. It grants it and returns a pointer to it, right? Malloc doesn't care how you're going to use how you use the memory. It's yours. It is yours. Do with it what you will. It doesn't care that you're going to use this to store integers. It doesn't care that you're going to use this to store doubles. It doesn't care that you're going to use this to store something else. It just says, okay, you want 500 bytes, or what was it, 400 bytes? There you go, it's over there, right? Do with it what you're going to do with it, right? If you're going to store 100 integers, fine. If you're only going to store 200 doubles, that's fine too. I don't care. That's your memory, right? However you want to use it. So it's yours to do with it what you want. And if you start abusing it, then things start to happen, right? Then the operating system says, wait a second, I gave you 400 bytes to use for these integers. You tried to treat it as a space where you could use 400 doubles, right? In other words, you wanted 800 bytes, but you only asked for 400, right? And you're starting to write memory that doesn't belong to you. Nope, segmentation fault. Right? You try to access memory that doesn't belong to you, that was not allocated to you. That's when it detects that and starts killing your program, like we've seen before. Right? All right. So why was malloc designed like this? We only need one malloc function. If it returned a specific pointer type, we would need dozens and dozens of malloc functions. We would need one for malloc for integers, right? We would need one for malloc for double. We would need one for malloc for char, malloc for whatever, malloc. Anytime that you created a brand new user type, which we'll do when we eventually get to structures, you would need to rewrite the entire standard library in order to have all the same functionality that you have with this one malloc. Right? You simply ask it for a chunk of memory, be responsible about using that chunk of memory, and you'll be good. Right? So let's look at an example of how to use it. A demo. Right? So let me come over here and let's go ahead. That other one failed when I created something that was 5 million, or was it 5 million? Yeah, 5 million integers. Create a dynamic array that can hold 5 million integers. Right? All right, so I'm going to have to call malloc. Right? Malloc returns, remember, a generic void pointer. So I'm going to have to capture that value. Right? If I'm going to treat this as integers, what kind of pointer do I want then? An integer pointer, right? How do I declare an integer pointer? This is just a retread from last week. Int star, and then give it a name. Right? I could call it pointer to a, right? But this is no longer a pointer. This is an array, right? Or ARR for short, right? Or numbers, or whatever you're doing here. I'll just go ahead and go with array for now. I'm going to call malloc here. But now remember when, do we have an example? Yeah, let's just think of an example from when we tried to do division. If I have an integer divided by an integer, is that going to work? 10 divided by 20 in either language. What will that result in? 0, because of integer truncation. Now, what's the solution for that? I do want to take 10 divided by 20, and I want it to result in the correct answer of 0.5. So what do I do to at least one of those values? I do a type test. If malloc is giving me this generic void pointer, I'm going to typecast that into the correct type of pointer that I want. So I'm going to typecast that as an integer pointer. Okay? Now, how many bytes do you want? Number of bytes. If you want 5 million integers, let me go ahead and put that into a variable here. 5, 1, 2, 3, 1, 2, 3. There we go. All right. Tell me, what's the math here? 5 million, 1, 2, 3, 1, 2, 3 times, how many bytes does an integer take again? 4. Right? There's the raw math. But remember, I already put my size over here into a variable, so I don't have to repeat that. Oops. It would be really nice if I could put this into a variable, right? 4. How many bytes? In fact, it's even better if you use what's called a macro that's defined in the standard library over here. Size of int. Size of int tells you exactly how many bytes an integer takes on that system. This is actually necessary because there are some systems in which things are not 4 bytes, right? Really, really old or arcane systems. The C standard actually says that an integer only has to be a minimum of 2 bytes. So you could be a completely compliant C compiler programmer, and all of your integers are only 2 bytes. You can only hold at most like 32,000, right? It's kind of useless, right? But then again, 2.147 billion is kind of useless, right? That's a limitation that that you can't go beyond, right? But in any case, I don't know how many. If I want to write interoperable code that will work on this system and that system and any other system, I should be using this generic size of, right? How many bytes does an integer take? Size of int. Right, there we go. All right. Once you're done, once created, you can treat it like a regular old array. I'm going to go ahead and set the first one. Array sub 0 is equal to 42. And let's set the last one, set the last element. So array sub 4,999,999 is equal to 101. Is there a better way of doing that? N minus 1, there we go. Set the last one, right? Let's go ahead and see this in operation. It'll work perfectly fine, right? Let's run it through Valgrind. Are there going to be any errors here? Oops, there's one error. What's wrong? Oh, I know what the error is. Don't worry about that error yet, though. Right? Well, actually, with only 5 minutes here, let's go ahead and look at the error of here. Yeah, here. Heap summary. Now we know what the heap is, right? The heap is this additional memory location over here that is much larger than the stack, that we can hold more stuff in. In particular, we can hold 5 million times 4, 20 million bytes in it that we couldn't hold in the stack before. In fact, it tells us you allocated 20 million bytes in one block of memory. Okay? You allocated it, but you didn't free it. 20 million bytes in one block are definitely lost. What does that mean? So we didn't lose memory, right? We didn't allocate memory, like physically, the RAM didn't stand up and start walking away, right? What happened here was we have a memory leak. A memory leak is where you create memory, you do something with it, but then you don't clean it up, right? You don't clean up after yourself. So what we need to do to make sure that this program works without any errors through Valgrind is we need to give that memory back. This is a preview of what we're going to look at next time. I'm going to free that memory up, array, because I'm done using it. So run this again, and you'll see that there are no memory leaks at all anymore. 0 errors. Right? You have to be good stewards of your resources, right? That if I write a program that allocates 20 megabytes, right, and then I'm greedy about it and I never give that, I'm done using it, I'm not going to give it back though, right? What's going to eventually happen if I just keep doing that over and over and over again? I allocate 20 megs, 20 megs, 20 megs, 20 megs. I hoard it all. I never give any of it back. What's going to happen to the system eventually? It's going to grind to a halt, right? It's less and less memory will be available for actual processes that are actually doing things, right? Eventually you will run out of memory, right? eventually. What will happen before that will be that the entire computer will eventually, get slower and slower and slower and slower and slower. It hasn't happened for many, many years, but well, here's a little bit of a history lesson. How many people use Chrome? Okay, about a third. How many people use Firefox? Okay, wow, a minority. That's where we are today. Yep. Other? What? Safari? Opera? Edge? Brave. What? Brave. Oh, okay. Brave. All right, so a little bit of history here. When Microsoft, it wasn't called Edge, but Explorer, when it absolutely sucked, Firefox came on the scene because it was a much better browser, right? Firefox then became notorious for memory leaks. This is a long-running process. If you've got your web browser open, you're probably not. It's probably open for hours on end, right? And if it's open for hours on end and it keeps accessing memory, creating memory, allocating memory, and never giving it up, that's called a memory leak. It eventually would grind your operating system's performance down to a halt, right? Firefox used to be, many, many years ago, used to be notorious for this, right? So notorious that Chrome came on the scene with a little bit better performance and took over the browser market to the point where Firefox, as we just saw, is now a minority market share, right? About a year or two ago, I switched back to I was on the Chrome bandwagon with everybody else. About a year or two ago, I switched back to Firefox for privacy concerns. And a year from now, when all of your privacy software is no longer working on Chrome, right? Then hopefully people will start coming back to Firefox as well, right? I've got what do I have here? Privacy Badger, Ghosterly, DuckDuckGo Privacy Essentials, Ad Blocker Ultimate, uBlock Origin, and that's just the YouTube enhancer, right? So I only mention this stuff because I was actually at a conference this summer, and somebody looked over on my computer and saw that I was your YouTube looks different. I go, yeah, what do you mean? And so we got into a discussion, and I was just under the assumption that everybody installed ad blockers everywhere, right? But shut your. Apparently, this is not the case, right? I had told him I haven't. I was. You tend to forget that YouTube has ads. I said. Like the one thing he noticed was when we were watching the YouTube, like, oh, where are the ads? Did you skip those already? I go, ads? I go, oh yeah, that's right, YouTube has ads. I haven't seen an ad in like 5 years, right? Because of this stuff. And literally, I've never seen an ad on YouTube. I would have to shut this, if I ever go to somebody else's computer and I start using their computer, or I go on the TV where there is no ad blocking software, like, oh my God, how do you live your life like this, right? Five ads before you actually get to the video that you want to watch, right? The point of this was, at some point, they fixed their memory leaks, right? And the performance of Firefox is great now. What did they do to fix their memory leaks? They probably just had to run Valgrind and find that they were losing memory at some point, come back in and add this one line of code. Once you're done with playing with your toys, what do you do with them? You put them away, right? Once you're done using your memory and screwing around with whatever you're doing with the memory, you free it up so that other people can use it, right? Take back your library books, whatever analogy you want to use, right? All right, any questions? No? All right. Then we will continue that on Wednesday then.